Hi, my name is Jamie Stout.
And my name is Clara Merciowski.
We recently conducted our final experiment in Chemistry 162, where we identified an unknown solid using methods learned throughout the semester.
The first thing we did was observe the solid. It was a finely ground white solid that resembled snow. It also appeared crystallized.
There were 6 methods available to use for identification purposes: thin layer chromatography, Fourier transform infrared spectroscopy, absorbance spectroscopy, nuclear magnetic resonance, gas chromatography, and mass spectroscopy. We decided not to use TLC and AS.
TLC is used to separate components of a mixture based upon the differentiating characteristics, the strength of intermolecular forces between the molecules of the substance, and the stationary and mobile phases. The analysis can be used to determine the number of components of a substance and the strength of the intermolecular forces in relation to other substances in the mixture. Because we were told from the beginning that we had a pure substance, we did not need to run a TLC plate.
We also decided not to do an AS. AS is observed on an absorbance spectrum that shows the differentiating characteristics of the lambda max, or the wavelength at which molecules absorb the most photons. This can tell us how much and what types of electromagnetic radiation are absorbed because each substance generally has its own specific lambda max. It also is more quantitative than FTIR because it distinguishes between the lambda maxes of multiple substances within a mixture. However, we did not use this method for identification because we were not concerned with what wavelengths are absorbed by our substance, as this would not help in determining the structure of our molecule. Once again, we also already knew that we had a pure substance, so there's no need to distinguish between lambda maxes.
The first method we chose to use was NMR 60 Hz. NMR is essential to determining the exact structure of a molecule. Its differentiating characteristic is the placement of hydrogens on the structure of a molecule. It shows how many environments of protons, or hydrogens, there are in a molecule, as well as the number of hydrogens in each environment. We used this method for identification because we wanted to be able to report the exact structure of our molecule.
The second method we chose to use was GC. GC relates the frequency of molecules in a substance to its retention time, or the amount of time it takes for the substances to exit the column in the gas phase. This differentiating characteristic is the strength of the intermolecular forces. If the forces are weaker, the substance will have a shorter retention time. If the forces are stronger, the substance will have a longer retention time. This tells us the relative strength of the intermolecular forces within a substance, as well as the number of components to a substance. While this was not extremely important to our identification, we submitted the sample to run the very necessary MS.
MS, our third method, is a technique used to determine the total mass of a molecule of a substance as well as that of major fragments. In this way, MS also helps to determine the structure of a molecule. Its differentiating characteristic is the molar mass of a molecule. We used this because determining the molar mass is vital to determining the formula of our molecule as well as its general structure.
Our fourth and final method for identification was FTIR. FTIR uses the differentiating characteristic of bonds present and not present within a molecule. Once again, we used this method to aid in determining the structure of the molecule in terms of what bonds there are.
Our NMR spectrum was the least reliable of all our data. One of the signals was below 0 ppm, so we worked with what we had. Our spectrum showed 4 signals, one representing chloroform D, our solvent, and the other 3 representing the 3 environments of our molecule. Our signal C had 1 peak, indicating 0 neighbors, with 0.23 integration or hydrogens, and a shift of negative 0.02 ppm. Our signal B had 1 peak, indicating 0 neighbors, with a 0.64 integration or hydrogens, and a shift of 2.32 ppm. Our signal A had 7 peaks, indicating 6 neighbors, with a 1.0 integration or hydrogen, and a shift of 7.32 ppm.
Our gas chromatography data showed 2 main peaks at 3.491 minutes and 5.775 minutes. Since the 5.775 minute peak is higher, we can assume that more of the particles in the sample had this retention time. Therefore, we decided to more heavily analyze the MS data that corresponded with the 5.775 minute retention time.
In our MS, we noticed that the molecular mass was 138 mass over charge because it is the largest mass furthest to the right of the spectrum. The largest peaks indicated the most abundant fragments. In our spectrum, the three largest fragments were at 43, 92, and 120 mass over charge. We used our knowledge of corresponding structures to help build the molecule. Here are the most frequent fragments of our molecule.
We analyzed the results of the FTIR and found many present bonds. There is a peak at about 2,900 inverse centimeters indicating a carbon-hydrogen bond. There is a peak at about 1,700 inverse centimeters indicating a carbon-oxygen double bond. There is a peak around 1,600 inverse centimeters indicating double bonded carbons. Finally, there is a peak around 900 inverse centimeters indicating a carbon-carbon bond.
So, a summary of our data includes the following. Our NMR showed 3 hydrogen environments. 2 environments had 0 neighbors, and 1 environment had 6 neighbors. Our GC showed retention times of 3.491 minutes and 5.775 minutes. Our MS showed a molecular weight of 138 mass over charge and major fragment weights of 43, 92, and 120 mass over charge. Finally, our FTIR showed the bonds present to include carbon bonded to carbon, carbon double bonded to carbon, carbon bonded to hydrogen, and carbon double bonded to oxygen.
This also means bonds not present include carbon bonded to oxygen and oxygen bonded to hydrogen. Based upon the data just stated, we claim our substance to be C9H14O, also known as 4-acetyl 1-methyl 1-cyclohexane.